because none of the points are actually on my license.
Yeah.
Okay, so notation. I want you guys to be comfortable with this because, again, it's something that's typically brushed over with sometimes when this course is taught. So this here is just y prime, and it doesn't really specify the independent variables. It just says y prime.
Oh, that makes sense. No,
Yeah, I
that's
thought it was
not
right.
standard.
It's spelled wrong, but it's not.
So it says, nice and brief, but does not name the independent variable.
Like,
No, I know. I
with
just
respect
wrote-
to-
Isn't
Yeah.
dy over dx the thing for derivative?
So this would have the same meaning, this dy over dx
Annotate it like that,
would
yes.
have the same meaning as this, except this gives a little bit more information. It's saying, you know what the independent variable is, you know the independent variable is x. So has the same meaning. A lot of times you'll just do this if you have y already written in terms of x, and then you want to write y prime. Y prime is the derivative of y. So let me write that as well.
Excuse me. The bottom one, I'm a little confused on what that's.
Yeah, I don't know if
It's
it's
the derivative of y, so like if you have y equals something.
It's like, remember when we found the derivative and it didn't say like y equals this, it just found
Oh,
the
it
derivative
just
of
said-
this, and you wrote d over dx instead of dy over dx, and that's what it is.
So this is basically a shorthand way of writing this. If the independent variable was x, which typically it's going to be what you'd be doing with.
Okay, with respect or what?
So this one here, so that one's more detailed. It's saying, the book says this. I want to give you two different ones. So the book says dy dx, how you say it, or the derivative of y with respect to x. Okay, and this names both variables and uses d for derivative. Okay, another way you think of it, because we know the derivative is talking about instantaneous rate of change, you can say the instantaneous change in y with respect or per instantaneous change in x. So we're used to seeing the delta, maybe see the delta, the triangle symbol for when we're talking about some change, but not necessarily instantaneous change. So now we're using this d here. It's implying an instantaneous change in y.
Because yesterday we used f prime of x.
So this, and this all essentially have the same meaning. So if you let y be f of x, then all these really have the same meaning. It's just the way this is written, as the book specifies, it's kind of like telling you, okay, go ahead and take or find the derivative of this function with respect to x. Which you could also say it like, find the instantaneous rate of change of this function per instantaneous change in x. There's more than one way to say these. But they all essentially mean the same thing. I just want you to be comfortable with what the d means and the y, the d when sort of dy and dx, instead of just brushing it over. And this becomes particularly important when we start dealing with differential equations, and we have to do basically the partial derivative of each side, and then you want to write it as, say, dy dx. So I think it's important to at least go over notation and be comfortable with it.
Wait, is it excuse if you leave?
Okay.
It
Everyone-
should be
everyone
clear.
have this? Let's go on to, let me pause this real quick.
With the muscle.
Yeah.
All right, so notation. So I think you guys understand now that the slope of the tangent line is the derivative.
Yes.
Okay, so there's different ways to describe the derivative. You can say the derivative of a function is the instantaneous rate of change of a function at any point, or you can also say it is the slope of the tangent line at any point. Okay, so now what I'd like to do, and this is especially good for the AP Calc exam, is looking at example 3, where we're going to look at the graph of f prime taken from f. So we're going to compare them side by side. So on page 101. Page 101.
If the derivative is a slope, how is the derivative?
Yeah, so this is where it gets a little bit deeper level understanding here. So if you don't get this at first, don't feel too frustrated, because I just said that y prime is the slope of the tangent line at any point on a function. Okay, so slope can either be positive, negative, or 0. Okay, so if you trace along on page 101, if you look at y prime, if you trace along here, we have the slope is positive from 0 to 2. Let me go ahead and put it on here so that it's all in one thing here. Let's do, don't think I'm going to do need a grid here, so let's just do, let's go ahead and see, it looks like at 2. Oh, thank you. Thank you. You see it already?
It's less positive, and
You
so
see
when
it?
it
Ah,
becomes a negative
yes,
slope,
yes,
it's
yes.
below the.
Very cool, yes, good.
That's weird.
It is weird
It doesn't look
because
anything like
it's
it, like
like,
you would never connect those two.
well, you're gonna have to. Not maybe not today or this week, but eventually you will have to start to be comfortable with the connection. It is still a strange one to look at.
It has to be a long way, right? Yeah.
What is this? This is on page 101. We're going to be graphing, looking at the graph of y and the graph of y prime. That looks not as good as that one, but I think it will do.
A function and the derivative of a function.
Yes.
Okay. Isn't the derivative graph just the tangent line?
So again, the derivative is the slope of any tangent line at any point on a function.
So if you graph the derivative,
So let's go ahead.
That's just for one point. This is like the slope for the whole thing.
Mm-hmm.
Even though like.
Thank you. Very good.
oh, the derivative is going to be the same no matter what tangent line you use.
No,
The slope of the tangent line is going to vary depending on where you are, unless you had a linear function, but this is not linear.
So the derivative is different for every tangent line. So if you graph the derivative that you're using, isn't it the tangent line?
it's going to continue to change.
So we'll say this is y, and that
So
is,
like,
sorry,
so the
that's
slope
y
is
prime.
positive, right? And so it's above the 0. This is the derivative graph. And so it gets less and less and less positive because it starts to flatten out, and that's when it gets closer to the x-axis. And then it starts going down because it's a negative slope, so it's going to be below the x-axis. And as it gets more and more positive, it goes back up to the axis.
Kind of.
Okay, so on the left here we have the graph of y, and on the right we have the graph of y prime. So if you imagine, I wonder if I could, let me see if I can. Imagine if I drew a tangent line, several tangent lines. I go along y here. So would you guys agree, let's say right here from the start, that the slope of this tangent line is positive?
Yes.
Okay, so let's draw another one that's fairly close. Would you still agree that the slope of this tangent line at, say, I don't know, x equals 0.2 is also positive?
Yeah.
So you can see that we can continue to draw thousands, say hundreds or thousands of tangent lines. They're all positive until we reach what, a relative max or min. Here, at a relative max of the function y, what would the slope of this tangent line be at the crest of this hill? It would be 0. So that's why here, the point here is 2, 0. Because you can see here at 2, the slope of the tangent line is 0. And then moving forward, as we move forward, what do we notice about all these tangent lines? They're negative, 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 negative. Change in concavity, which we'll discuss later. You may have just seen it by the way I moved it, the change in concavity. Did you guys ever discuss concavity? Yeah, we'll discuss that later. So then we go, and then now it's negative until when? Until we go back to 0. So let's go back. So positive, 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 positive. Talk about the slope of the tangent lines. Positive, positive, 0. Negative, 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 0. And then it's going to continue. Now I'm going back positive. So you can see, okay, the slope of all the tangent lines, they were negative all the way until 6, where we have another a relative minimum on our graph of y. And then going past that, the slope of our tangent lines would be positive. So this is a more advanced concept, is being able to, let's say, especially if you were given this and you had to visualize that. That can be even a little more tough, which is important for the AP Calc exam.
I have a question.
Yes.
Will we ever have to graph a y prime function?
Not only will you have to graph the y prime function and be familiar with it, you will be given this on the AP Calc exam and expect to visualize that going the other way, which is more fun.
I don't know if maybe I just don't know it yet, but like I'm confused on how, like I understand the concept, I just don't know how that works.
Okay. So I have an idea here.
Like how would you graph them?
This might be a more simple example. Let's do this. This is a different example. Let's go with something that you guys are definitely familiar with. Let's go with green. Does it feel like it? And well, then we're not going to do that. Let's go with something. Well, that didn't work. And just change it. How's that? Better? Okay. So let's go back to here. Let's go to black. And we'll say, actually it's like almost perfect 45, so let's go with that. Say this is 2 and 2. Okay, so maybe you guys can figure this one out pretty easily, more simple. So if this were the graph of y, what do you think the graph of y prime would be? You think it'd be the same?
No, it would be the top. I don't, I'm just guessing. Yeah.
So let's think about this. The derivative gives us the slope of the tangent line at any point.
I don't understand.
Of all the tangent lines, to be more clear, it's the slope of, like when you graph it, you're graphing the slope of all the tangent lines across that whole domain.
Tangent line stays
What
the
would a
same, though.
tangent line of that look like?
Yeah,
There are different tangent lines you could have.
Isn't it
Like
just
on a
running
curve,
through
there
it
are a bunch
once?
of- You could pick
So
any
isn't it
point
like
and draw a tangent line from there, so there are a bunch of possible tangent lines.
So let me say it another way, because I'm going to keep doing this because I want this to be good, solid in your mind. The derivative is the instantaneous rate of change of a function for any point of the function, assuming it's a differentiable function.
The rate of change is the same for all points, so it's just gonna look the same.
No, you were close. The first part you said was right.
How would it look different?
First,
It's
no,
the
did you know what you
same.
said the first time? And that was correct. Do you guys
It's a
agree?
constant rate of change.
Yeah.
It is a constant rate of change.
Okay, so it's gonna be a
What
line.
is the rate of change at any point along this function? It is. So, this guy would look like that. Would look like a horizontal line at 1.
Oh, okay.
That makes sense.
Wait, say that again?
Because the rate of change is 1 the whole time.
This might be an easier thing to grasp before you deal with graphs that involve curves. But then once you understand this, you should eventually try to grasp and need to eventually grasp, something that's not linear and then maybe polynomial.
So do you graph something like the prime function just by plugging in? Like how do you do that?
Okay, so good question. So how could you graph? Okay, this was fairly easy because the rate of change, the instantaneous rate of change, never changes. It remains constant at 1, which this one was easy. So you might, you're probably more concerned about something like, oh, what about this? How could I do this? What you'd want to do is you'd want to graph we'll call them I don't want to call them critical points. Yeah, key points. There we go. So key points. We know that the slope of the tangent line at maxes and mins is 0. So I would plot those. Boom and boom. And then you got to kind of just think here. Okay, the slope is positive as we move along heading towards 2. The slope is still positive, but is it as strong? In other words, is it decreasing the slope?
Yeah.
It's still positive, but it is decreasing. And that's the mentality you have. And just make it smooth. Just make it smooth. Obviously, there's an infinite number of points from, any point to another point. So you only just need to graph, just like when you graph anything, growing up in math, you graph a parabola, you graph maybe 5 points to graph a parabola. You graph it's impossible to graph every single point by hand. Even a calculator doesn't do every single point. It may do like 1,000 points or something like that, or 10,000 points, or however it's programmed.
It's possible to reach a emergency conscience in your mind or
I don't know what you're talking
I
about.
don't know either.
Let's keep it.
I just like knowing this.
Let's keep it simple. There are an infinite number of points that make up a function between any 2 points. But you're not going to be able to graph an infinite number of points, nor do you have time to graph 100 or 50 or even probably 10. But I would graph definitely this guy, key points, thank you. This, and then just make sure it's smooth. And then you have, so you graph these 2, but then you have to think, okay, does it go like this? Does it go like this? And then that's when you have to think intuitively, okay, the tangent lines would be positive, and they are, the slope of the tangent lines are positive, but they are decreasing, and then they go to 0. And then they start to get negative, and they get even more negative. They get even more negative. And about this here, now this is the part, this is the part we'll discuss as we go deeper, but I'll mention it now. This guy's relative min is a change in concavity on this guy.
Yeah, that makes sense.
What is concavity?
It does make sense to you?
Well,
Sort of,
like
kind of?
knowing what concavity is, you can see where the slope starts to it's getting more negative and more negative, and then it starts to get less negative. So that's where
So concavity, which may be a new term for some of you, should definitely be mentioned when teaching, say, Algebra 2 when you're graphing quadratics. It should definitely be mentioned because it's important. So quadratic. So imagine if to help you visualize it, if I extended this guy. Now this is obviously not actually part of the function I'm drawing, but let's say I extended this guy. You could see that this part has the general concavity of a negative concavity. And then if I extended this guy would have a positive concavity. Now you can kind of see it when I did it with the ruler. Watch where you have this, it's even hard to describe in English what changes come, but if you see it, you'll see what happens with the ruler. So let's say you're on like a roller coaster, right? And this is going up, okay? Goes up like this. And then watch the change in concavity when it goes like this. You see that? Watch that again. So this is going up like this. It's almost like you're being lifted out of your seat on the roller coaster, and the change in concavity is when you're now being pushed into your seat, right there. That's the change. Now you're being pushed into your seat on the roller coaster. That's change in concavity. Yes?
So it's only going to go below the x-axis when your original function is going down, right?
When it's negative slope, yeah.
Yeah, so notice here, what this is
Anything that's
saying.
going up is going to be above the x-axis, and anything that's going down is going to be below. It goes back up, so you know it goes back
Yep, you
up.
can see that. Very good. You can see that. From 2 to 6, you can see that all the slope of all the tangent lines would be negative, as it's shown here. I'm just taking it one step further, and if this feels like a lot, I'm just giving you. We are going to go. Concavity was going to come later, but I'm just touching on it now because it is relevant. So I'm just pointing out where this guy has a relative min or max is a change in concavity on this guy.
So what would make it what would make that min bigger, like smaller?
What would make the min?
What would make the minimum of the prime graph smaller?
Like more negative?
Yeah.
Well, if this guy was increasing more slowly, because think about if this guy was, let me just go ahead and draw it. If this guy was only increasing like, say,
Would it be if it increased more?
this, because the slope is getting to 0 more quickly, so this guy would be even sharper, which may shoot down further if that helps.
Okay.
Yeah.
Wait, it would be sharp. It would be steeper.
Yeah. So let's keep going. So it kind of like a real broad hill. So this guy is not going to reach, not going to have a tangent line with a slope of 0 for a while.
Wait, wouldn't that make that?
Sorry. That's until it hits a 2.
Would it that?
But then it goes negative. So I don't want to make this too confusing. I don't want to go too deep because I want to give you a little taste, because it's only
Yeah, can
47.
you draw the prime graph of that function? I just want to see what
Of this orange? Okay. So this orange basically starts off with the slope of the tangent lines are positive. And it is,
They slowly.
no, it's even more quickly going, well,
No.
how would you describe this? So, let me get rid of this. So we have this going on.
So
It's
then,
not going
I'd like
to, it's not going to reach,
start
so
getting
let's say it's max, the relative max is there,
Right.
but this guy, and then it didn't, so it doesn't hit 0 until like, just after
Until
6.
like 7.
Just, yeah.
So
So
it's
this,
gonna be a lot
this guy,
less steep.
yeah, this guy wouldn't hit 0 until like at 7.
Right. So it's not steeper.
The derivative?
Yeah.
Yeah, it would be less steep, correct. Good.
So
So it'd be, say, starting the same thing, but it's going to take a while. It's going to take longer.
Yeah. Because you're extra.
Yes.
uh-huh.
And so forth.
Okay, so I understand the steepness now, but I was asking about how far down that goes, and then
Well, it depends on how long how long until the change in concavity, because that's where the change in concavity occurs.
So
Now that's the one that's tougher to see. Remember,
So if it was like this.
That's when it starts going up again?
it's almost like if this part were elongated,
Right, yeah.
it would take longer until we reach that point of concavity after we've already reached the first max.
So it's how long until you reach the next min? How long until you turn up?
From zero for a derivative of having a derivative equal to zero until there's a change in concavity.
So basically, like you're saying, if it was like here, and then it like came up like that.
Can we
then,
define
like,
concavity?
Yeah,
Can you just tell
concavity
me
with the definition.
I guess it would have to come down like that.
What's that?
Like that's where that would make it longer if it didn't come back up until lower. Is that what you're saying, guys?
I'm saying that, imagine, okay,
Yeah,
let's just say,
yeah.
okay, let me do this.
The blue
I'll
line,
say this.
instead of going up right there, if it started turning up closer to the
This
x-axis.
portion here, imagine this blue portion here was longer,
Can you draw
This-
it like it's longer?
this guy would be going down further.
Can you draw it like if it was longer? What would it look like?
It would look like what you did.
Okay,
it would
like
be
that.
down.
Okay,
Like,
that's
like if
what
I drew the exact same shape, but I just made these like this, I call it a hill in this valley, like this. It just made this part longer. And you could imagine, okay, yeah, the slopes are negative, but for a much longer period of time until we reach this guy's min, which is a change in concavity. And this is a lot. Typically, we don't even go into concavity, but because you guys are kind of getting it, I'm kind of going with the flow, which is cool.
So the change in concavity is when the derivative is zero at a max, let's say right there.
The change in concavity is when the second derivative is set equal to zero. Which makes sense, because here's the first derivative. So the derivative of this guy,
Oh, the tangent line of the derivative, that makes sense.
yeah, that's the change in concavity.
Sorry.
So if you want the definition, an inflection point, which is where concavity changes, is when the second derivative of the function equals
What is
zero.
an inflection point?
Where a change in concavity occurs.
Okay, can you like define these words instead of just like, you know?
Well,
What
we're
is
not really
concavity?
going over it, going
So
over it.
where f prime equals zero represents an inflection point for a function is differentiable. Concavity is a tough one to define. The best way I can possibly describe it to think of it intuitively is to think about if you're on a roller coaster. Imagine you're on a roller coaster. You're on this roller coaster.
It's just like the change in concavity is the point when what changes? Like what is it that's changing?
The second derivative is going from negative to positive or positive to negative.
But what does that look like?
What does what look like?
Like what does a change in concavity look like? Like you, is it?
It's where if I were to extend these, the U's, you can see where this U general shape, the general concavity of it is down for the most part. And then when does it start to kind of phase out to where you can no longer see, from whichever direction, from where it's no longer a general shape of an up and no longer down. It's,
So this is the change in
no,
concavity?
it'd be more like right around here.
You know, do you remember we did the second derivative, and if it was positive, it was a minimum, and if it was negative, it was a maximum in a function?
Yes.
So there, the slope starts to become,
Be careful.
maybe, I don't know, I'm not sure if I'm going in the right direction. Can you tell me?
Where the first derivative is equal to zero is where there is a relative max or min for the function.
Okay.
But where the second derivative equals zero is where we have an inflection point. So I'll write these out since we're discussing it. Let's go to another slide and we'll write this out.
It's not, just look it up.
So it's definitely
Is it concave down and-
concavity better be in this book.
It's definitely not
It better be
in the glossary.
in the book.
There's
Okay.
a concave up and a concave down.
So
Is that-
where
Yeah, but.
y
the change in
prime
concavity is
equals
when you change from up
zero.
to the down, so I don't understand what it is. What else could it be with?
Wait. He said that's not what it is.
He said
A
it is
relative-
not when you change. I was thinking like, if this concavity is this way and then you change to one that's this way, the change is when you change to this way. That's not it.
I think you're on the right track, it's just not quite, it's not that low. It actually changes higher up, but it doesn't really look like it changes higher
Oh,
up.
it's just, he
Like
just.
the middle of the
Yeah.
red, where the
But
red
it is
circle
that
was.
concept.
Yes. Okay.
Oh, I was like,
Okay.
so.
Concavity.
So it's basically when it's
Leave
a
it
vertical.
zero.
Yeah.
Do you wanna?
But not, it's not, doesn't actually get vertical, it's when it starts to change the other way.
It's when the slope is vertically zero, that's the changing.
Think about it, it's getting more and more negative, right? As it comes down, it's gonna get more and more and more negative. When it starts to get more positive, that's the point when it's concave.
So then the slope line is gonna go like that,
Yep,
and then
it's
like.
more and more and more negative, and then but it may not get completely straight up and down. It might get there and then start to go back up more positive. See where your arm like starts to go back up positive? That's what it is. Yeah.
It's here, and then.
What's that word?
So it's when the slope,
Extremum.
so it's when the slope starts,
Extrema is plural.
it's when the slope.
I think that's right. Yeah. If not, I'm being creative.
When were the, no, I think is the singular and is the plural.
Extremum is the singular, yes? Extrema is the plural?
Yes.
I have a question. When would y prime be zero? Wait.
Y prime would be 0 when you think about if you graph all the tangent lines, like visualize them. When the tangent line is horizontal, the slope of a horizontal line is 0, so that's where y prime would equal 0.
That maxes in the.
Max is in the min.
Oh, that just makes sense.
Concavity is definitely more difficult to see than extrema.
I think I understand now.
But algebraically,
Yeah.
it's actually non-graphically it's a lot easier to see. You just take the derivative and take the derivative of that, set that equal to 0. Oh, that's where tangent concavity occurs.
Yeah, that's what I was trying to say. This is
Mine was the
that's
other
what I
there,
remember.
find out which one it was, yeah.
Very good.